Have you ever stopped to think about the physics behind something as simple as pushing a pin into a corkboard? Well, today we're going to dive into two concepts that are all around us every single day: thrust and pressure. They explain why a sharp knife works so well and why a huge tractor doesn't just sink into a muddy field. Let's get right into it.
So here's what we've got on tap. We're going to start with a little puzzle I like to call the thumb and the pin. Then we'll get clear on what thrust and pressure actually mean. After that, we'll look at the simple formula that ties them together, see how these ideas show up in the world all around us, and wrap it all up with the one big takeaway you'll want to remember.
All right, first up, let's start with a really simple thought experiment. This little puzzle is the perfect way to frame everything we're about to talk about. Okay, picture this. You take your thumb and you press it against a wooden board with all your might. What happens? Not much, right? You just get a little indentation on your thumb. But now, take a drawing pin and push with that exact same amount of force. It slides right into the wood. So, what's going on here? The force is exactly the same, but the result is completely different. Why?
The answer, the entire secret, isn't about how much force you're using. It's about how that force is spread out. The key to solving our little puzzle is all about the area the force is acting on. To really understand that, we need to be a little more specific with our words. So let's officially define the two key players in this story: thrust and pressure. First, let's talk about thrust. All thrust really is a fancy word for a force that's acting perpendicular, meaning at a perfect 90-degree angle to a surface. So when you push your thumb straight against the wall, that direct, straight-on push, that's thrust. And since thrust is just a specific kind of force, we measure it with the standard international unit for force. You've probably heard of it. It's the Newton, and we represent it with a capital N. And now for the really important one, pressure. Pressure is what you get when you take that thrust, that force, and you measure how much of it is acting on every little bit of an area. It's not just about the total push, it's about how concentrated that push is. So, what's the unit for pressure? Well, the standard SI unit is the Pascal. We write that with a capital P and a lowercase a.
And a Pascal isn't just some abstract term. It's defined very precisely. 1 Pascal is the amount of pressure you get when a force of 1 Newton is spread out evenly over an area of 1 square meter. See? It's right there in the definition. Force divided by area.
Okay, so that brings us perfectly to the simple but incredibly useful formula that puts all of this together. And here it is. Pressure equals thrust divided by area. It's that straightforward. What this little equation tells us is that pressure and force go up together, but pressure and area have the opposite relationship. Let's just quickly review the pieces one more time. We've got pressure, which is force per unit area measured in pascals. We've got thrust, which is our perpendicular force measured in newtons. And we've got area, the space the force acts on, measured in square meters. These three are all connected by that simple formula. And this right here is why our little puzzle works. It's the big reveal. On the left, with your thumb, you're applying a force over a pretty large area, so the pressure is small. But on the right, with the pin, you take that exact same force and you focus it all onto that tiny, tiny point. The area becomes incredibly small, which makes the pressure absolutely enormous. And that is why the pin sinks into the wood.
Now, this isn't just a neat physics trick. This is a core principle of design and engineering that you can see literally everywhere once you start looking for it. Let's check out a few examples.
Sometimes the whole point is to create as much pressure as you possibly can. Think about a sharp kitchen knife. Its cutting edge is incredibly thin, a tiny surface area. So even a small force from your hand creates a massive amount of pressure.
enough to slice right through a carrot. It's the same idea with a nail. That sharp point concentrates the force of a hammer blow into an intense point of pressure that can easily get through a piece of wood.
But just as often, the goal is the complete opposite: to make the pressure as low as possible. Why does your school bag have wide straps? To spread the weight out over a larger area of your shoulder. More area means less pressure, which makes it much more comfortable. It's the same reason tractors and army tanks have those huge wide tires or tracks. They spread their massive weight over a giant area, which lowers the pressure and stops them from sinking into soft ground. Even the foundations of huge skyscrapers are made wide for the exact same reason.
So, after going through all that, what is the one single idea that you should really hold on to?
It all comes down to this one simple sentence. The effect a force has isn't just about how strong the force is. It's all about how concentrated that force is. That is the key idea behind everything we've looked at today. So, the bottom line is this. If you want to control pressure, you have to control the area. Want more pressure? Make the area smaller. Want less pressure? Make the area bigger. It's a simple relationship that designers and engineers use all the time to do some pretty amazing things.
So I'll leave you with a little challenge. Now that you know this secret, the relationship between force, area, and pressure, just take a look around you. At home, outside, anywhere. How many things can you spot that are intentionally designed to either crank up the pressure or to spread it out and reduce it? I promise once you start looking, you'll see it absolutely everywhere. Thanks for tuning in.